Okay, so this week we're going to just step through Module 13. There's a couple of topics here. This is really the last new material I'll be showing after the assignments this week. The only thing really is final project, proposal, completion. I have a progress thing in there for next week where you can give me a status report on where you're at with your project. So this is really the last of the new stuff I wanted to show you this semester. Again, this is, I believe, the same as what you'll see in Blackboard, but I'm going to try to step through what each one of these things is doing so you can see it firsthand, and then I'll try to explain some of the last assignment to give you an idea what I'm trying to go for there, although some of you have already turned it in. So this isn't broken down into topics very well here, but in the first one, I'm just trying to show writing and reading from a queue, because the overall topic here is kind of a data pipeline. Now, data pipelines, we could do an entire semester on dealing with processing data and real-time processing and doing it quickly and things like that. But you're going to get the short version because we've really just got this 1 week to go over this stuff. So I just want to show you kind of some scenarios where we're going to essentially do it. I wouldn't think you would typically do it this way in the real world. I mean, why would you write code that creates a queue of things and then in the same snippet of code takes it back out of queue? That doesn't make a ton of sense, but just to kind of show these processes running. So in this first one, all of these are going to be run, I think, entirely via command prompt. These kind of programs don't run well in Jupyter notebooks. Some of them work, some of them don't, but I'm just not going to mess with it. I'm just going to explain it here, and then I'll go over and run it separately. So this first one, I've got 2 processes that I'm going to run concurrently using multiprocessing, which we got to learn a bit about last week. And you can see the first process here is going to create a queue of numbers. And I put some limiters in here to keep it from running infinitely because I didn't want it to run all day. But you can see the first one, it's called give slow numbers, and then it gets passed a queue because part of this is sharing a queue between 2 processes. And while that counter is still greater than 0, you can see I've got a counter of 1,000. I put a fake delay in there to slow things down a little bit. And then down here, kind of skipping around here, I actually created a size limit on my queue. Now, if you don't have to have a size limit on your queue, they can be infinite, as you probably already know. But I just wanted to show a max size in a queue. And in real-world scenarios, you do typically want to, in most cases, have a max size for a queue because it can be a warning when some downstream process has stopped functioning. So all of a sudden you've got a queue, let's say you've got a queue that can hold 10,000 items, and it never hits 10,000 items because your downstream processing continues pulling things off of that queue. Well, all of a sudden that queue hits 10,000, it can raise a flag, and you can figure out what's gone wrong with your overall architecture. Why it's either things are getting passed to the queue faster than they normally would, or things are not getting pulled off the queue like they're supposed to. So max size is a common thing. A lot of times, if you have a queue like this, you do not want to hit max size and then just stop, because the upstream data is still wanting to be written, and you're going to create issues uphill from your processes. So what oftentimes you'll see, at least in my experience, is you'll have something called like a dead letter queue. And what that really means is these processes attempted to run, let's say the queue maxed out, so then you started shuffling things off into a different location to store it so you don't lose that data, because it's really important that we don't lose that data in most cases, and you want to be able to get it back later, so you just want to store it somewhere while you're trying to fix the problems downstream, and then you'll figure out a separate process later to bring that data back in and pass it through the queue. It would be like a one-off situation while you were fixing your code. But in this case, I'm just putting a max size in here just to show the process having a max size. So while that queue is not full, I'm going to just put a random number between 0 and 10 in there. And then I'm going to decrement my counter. So that's what that process does. It just continually does that. The get slow numbers does the opposite of that. I again put a counter in here, so once all this is complete, the program can end, and I can say, well, my queue is not empty, print it. So really, on one side, I'm just loading things up onto the queue, and on the other side, I'm just pulling them off the queue. So kind of a very simple data pipeline. And then none of this down here should be new to us. I've created a multi-processing queue. I've set up process number 1, which gets past that queue. I've set up process number 2, which gets past that queue, and then I start both processes. And I don't think this will be anything shocking because it's just going to be a bunch of numbers, but it's called example1.py. Oops. Navigate. Can you tell I do this same thing way too often? Python. So essentially what's happening here is on one side, like I said, it's loading up that queue, and then on the other side, it's just reading off and printing that queue. And it'll do this until either one of them runs out of count. That's not on your screen, I'm sorry. Or is it? Yeah, it was. Yeah, it's there. So I wanted to put a couple of things in here. I put some special notes in here. I just put an output that says queue full whenever it has hit that 20. So I didn't have it in the code I shared. In my actual example that I saved here, you can see I didn't save this after I commented out. But it's saying if it runs into queue is full, it just prints queue full. I could have done on the other side too, saying queue empty, just to show those examples where I've read or I've loaded up the queue as much as I can. This code isn't perfect because in this case, if it's queue full, I'm just using up one of my counters. So in the end, I won't actually load 1,000 numbers in because I'm losing my counts every time it hits queue full. But I just wanted to show the scenario where the writing side has filled up that queue faster than the reading side is pulling it off the queue. I haven't done anything really new here. It's just kind of a simple example of putting the pieces together. Okay, so that's that one. Go back to my demonstration part here. Okay, so now let's do something a little bit more complicated. So in this one, I am using, I have to remember this. So I've got 2 processes here, and one of the processes spawns 4 threads. So you can see give slow number process spawns 4 threads that all write to the queue. So I'm combining multiprocessing and threading here. Oftentimes, if you're doing something like this with a data pipeline, upstream, you don't just have one source of data coming in. You typically have multiple sources. So for instance, if you're, the one I always go to is because it's the one I've got the most experience on, if you are pulling data down from multiple websites that you are managing user experience on, many of those would pull into a single queue for you to process. So you would have multiple upstream things loading into the queue with proper identifiers so you can separate the data out as you work through it in your data pipeline. So I'm kind of simulating that here. So one of the processes has 4 threads, and each one of those threads is just, again, throwing a random number onto the queue. And I've still got that max size on my queue from before, max size of 20. So each of those 4 threads is going to load, but if the queue is full, it's just going to print waiting for the downstream process to unload the queue. And then the other one is the same as before. So if my queue isn't empty, it just gets the number and outputs it. And I put those same counters in like I did before. So this one is threading with multiprocessing. My other program's still running, so I got to kill this. There we go. Oops. So there's nothing super special here. You see on the first 2 it said waiting because I was trying to pull off the queue. Or I was trying to load the queue and it was already full, so I had to wait. But again, same thing as before, but now I've got 4 different threads writing to that queue, and I've got one process pulling off the queue and printing it to the screen. Just showing how these different things can work together. Again, We know threading doesn't happen concurrently in Python, but maybe, again, that upstream data is you reading, scraping a website and pulling down some specific piece of information. Maybe you're trying to read all of Craigslist and you want to pull the titles for the listings. Well, you could spawn any number of threads to pull that data down, load it into a single queue for you to process through using your program. So just trying to give that kind of an example here. Okay, so that's that one. So that's what I wanted to show you, just handling queues in sort of a data pipeline here. The next topic in this module is generators. Generators are kind of one of those special tools, again, that they have a use, but you want to make sure you're using them correctly, because in a lot of cases they may not gain you anything. But generally, a generator can be thought of as a function that returns an iterator instead of a return. So the nice thing about a generator is you can run it, and then once you've gotten some piece of information off of it, it essentially pauses the process. And then when you go to utilize that generator again, it will continue from where you left off. Whereas a function, you run it, you get the same result every time. You just run it again, you get the same result, run it again, same result. Each time you utilize your generator, it just continues until the next time it is told to output data. And really the difference syntactically is a generator is a function that has a yield statement instead of a return statement. And anytime there is a yield statement, it does what the yield statement says. Like in this case, I'm saying, give me a variable out. It then pauses at that point. And then the next time you call it, it continues past that yield statement and runs again until it hits another yield statement. So here, I'm just going to step through this example. First, I'm going to create my generator here. It's called get 5 numbers. And then in this case, I'm just creating a list that I'm going to output. And I'm going to output it 5 numbers at a time. So I'm saying, well, the length of my yielded list is still greater than 0 because I'm going to pop items off of this list or take items off of this list as I go. Do this. So you first create a variable that is the first 5 items in the list. You can see 1, 2, 3, 4, 5, and assign it to a variable my yielded list get 5. And then I'm going to delete those first 5 items because I don't want to get them the next time around. And then I will yield those 5 items. So the first time this generator is accessed, it will give me this. The second time it's accessed, it will give me this. And the third time it's accessed, it will give me this. And you can see that it will continue doing this while loop until I run out of items in my list. And then the last time I added this isn't necessary, but I just want to show it. I can yield something different, saying, hey, the list is empty. There's nothing left to give. And then the next time it's going to give an error, and I want to show both scenarios there. So I've got my function or my generator created here. Now I want to utilize my generator. I need to assign it to a variable, and that is what will actually get utilized. So you can see here, I've got get 5 nums, my generator. I'm assigning it to this variable myGen. And then to get that generator to run, this is the syntax you use. You just say next and what you're trying to get from your generator. So I've got my generator created, and then I'm just going to print next myGen. And this is from when I ran it before. But the first, what have I done? Oh, I didn't run this one. There we go. Now my generator's set up, and now when I run it, you can see that it pulls the first 5 numbers from that list. And then I'm going to run that same cell again because my generator paused after I got those first 5 numbers. And you can see the second time it gives me the next 5 numbers, and then it yields. So the state is being saved in that generator each time I'm utilizing it. Third time it gives me the last 5 numbers. Now my list is empty, so that while loop in my generator won't run again. You can see now it's giving me that the list is empty, which you can see in my code there. And then the next time I run it, it gives this exception called stop iteration. This exception is pretty valuable because you can do a try except. And so you can try to utilize the generator, and if you get an exception, or you can specifically state if you get a stop iteration exception, then you can continue through your program. So it's an excellent way once you've if you have a generator that's not infinite, once you've exhausted your generator, you can continue through your program. Okay, so now I'm going to use this generator function to create an infinite prime number generator. So some of this code I stole on how to generate a prime number. I didn't try to figure it out. I'm not a mathematician. Probably could have if I'd spent the time to figure it out, but I just took this code from somewhere about how to figure out whether something's a prime number. So I created this function called isPrime. It accepts an input number or an integer, and it's if it's less than 1, false, because we know no number less than 1 is prime. If it equals 2, it's true. 2 is the only even prime, so it's kind of a unique case. And if it's divisible by 2, it's false, because there is no even prime number. And then this one, this is apparently how you mathematically figure it out. So if it's I is 3 and some square root, basically if it matches this, it returns false because it's not a prime. And then if none of these scenarios are hit, I just have it return true, because that means that it's also a prime. So that's generally how that function works. I'm sure we could derive that all works, but that's not the point of what we're doing here. Essentially this function determines whether a number sent to it is prime or not. And then I'm going to create a generator that basically takes those numbers and passes them into the other function and yields n if it's prime. So each time you call this generator, it's going to take the next set of n, it's going to keep iterating over numbers, and once it achieves a true from that isPrime function, it's going to return that prime. So every time I access this generator, it's going to give me the next prime number. So I'm going to run this again to make sure it's been run this again, make sure it's been run. And then just like before, you can see I have to do create a variable. I called it generator, which is a terrible name. And I'm going to assign that variable prime generator. And then I'm going to start accessing it. And I'm just doing it 10 numbers at a time. You see I already ran this to make sure it would run for me. So I'm going to grab 10 items by accessing my generator 10 times. And then I'm just printing it with bars in between to make it look nicer. So first time I get the first 10 primes. And then if I attempt to call that this same cell again, I get the next 10, et cetera, et cetera, et cetera, et cetera. So I've created a generator that allows me to just keep getting groups of prime numbers. Well, the generator itself gives me one prime number, but I'm just accessing it in a way that gives me a group of prime numbers. So that's kind of nice. Part of the question is the value, and I go over it in a little bit here. But one of the nice things here is that my generator and my program aren't necessarily storing all of these pieces of information. They're just storing the state. So I don't have all of this overhead of that's being stored. Now, storing 100 prime numbers, who cares? But there are cases where you grow this into a much larger scenario where you don't want to have to store all these large groups of information, because it's just overhead for your program. And I go over that, I guess, in just a minute. But here's a very similar example, just to show something maybe a little more interesting. I'm creating a big prime generator here. In this case, it's the same as the other one, except I pass it a variable that says how many digits I want to have in my prime number. So if I wanted to, I think I asked for it to have 15 digits in this example, but I send it 15, and then I piece together a number starting with 1, and then however many digits. So like if I said 5, it would be 1 with 5 zeros, becomes an integer and is assigned to that variable, and then it attempts to find the next prime after that. So that's how that generator works. If I run this, and then I've got my new generator assigned to big generator, and then when I run it, it's the same as before, but this is actually takes quite a bit longer because it's trying to determine with a 15-digit number, and actually I have this set to run forever, what the next prime is. And it will continue to run trying to find prime numbers for me for as long as I'm willing to put up with it. So if you wanted to find out, I don't know an example where this is useful, but if you wanted to find out what 15-digit number is prime, you wouldn't like start with 1 and work your way up. You could do something like this, I guess, and start with a 15-digit number and then continue from there. I'm going to do this so it doesn't keep making my computer hum. Okay, this is just a side note or something to be aware of, because we didn't really do a lot with lambdas or anonymous functions, but you can create generators in a similar way to anonymous functions. Just something that you should know, because you might run into the code online, or you may want to do the shorthand version of it. So, and this is also an attempt to show the value of a generator. So this first one is, this is a, basically I'm creating a list of the square of an integer I for the first 10,000 numbers. So I'm squaring the numbers from 1 to 10,000, and it's stored in a list. And then I just print it because, and then I print the size of it. And this is where I'm trying to show a little bit of value here. That's the old way, I guess, or the way we've seen previously. Here, I'm doing the same thing, except I'm using the syntax that is creating an anonymous generator. You do it like it would be a tuple instead of like a list. And you can see it's the same code inside. It's going to have the square for I in range 10,000, and then I'm going to do the size of it, and then I'm going to print it just to show you the difference. And you can see down here, I get the first one generates all of this, but the second one, or the first one, has a size of 87,624 bytes. This is the size of my generator, 120. And when you print it, you just get a generator object, because I didn't actually utilize the generator. So when you're sitting with it at rest, I guess the point here is that it's a much smaller thing. Again, there are cases where this makes a lot of sense, but there are a lot of them where processing speed makes these kind of things unnecessary, and storage capacity makes these things unnecessary. But if you are trying to create, let's say, an infinite iteratable, which is not possible, you can't make an infinite list. You could do something like a generator, where you could have your iterator there, and as you access it, you just have the next item in the iterator forever. So you could continue to utilize it without having to attempt to store infinite numbers. Do I have? Oh, I guess I have another example yet before. This is just, there's nothing special here. I'm showing utilizing the generator. Okay, so this last one, just to show you, I'm not a huge fan of these kind of things, because I think they cause more confusion than anything. But again, you might run across it. But you can pipe them together or stack generators. There may be a time when you want to do this. But I've got 2 generators here. The first one becomes a number generator, essentially. So however many numbers I request on the input, it yields those using a for loop. So each time it gives me one random number up until however many I run into. And then the second one takes an input and squares it and yields it. If I stack them together, I can get 100 numbers, square all of those numbers. So you can see it's first it's creating the numbers, then it's squaring the numbers, and then I'm summing the numbers, and then I'm printing it. So I can pipe these things together, and each time I run this, you can see it's going to give me a different number because it's a randomizer. But it's just something you can do. At no point am I really storing these 2 sets of 100 numbers. I am just utilizing a generator to iterate through them, summing them up and getting the result. Okay, that's what I wanted to show you with generators. Okay, so this is the data pipeline part. So this is the last topic, and this is kind of setting the stage for the last assignment this week. So I'm going to step through and do simpler and work my way to more complex. I'm going to use a generator function here just so I can tie it in with the previous topic. What that generator does is it opens a Tale of Two Cities text file that I have in the same directory as my program, and for each line in the book, I'm going to cleanse it of everything that is not letters or numbers. Output string, yeah, so anything that's not letters or numbers, I get rid of them and I replace them with a space. So if there's weird punctuation, I just get rid of it. And then I look for a line that says end of a tale of two cities. If it runs into that, it raises an end of file error. And if it doesn't find that, it looks for the word chapter. And if it doesn't find chapter, then it will take each word, split it out, and put it into the queue. So that's really what that function does. And then once it runs out of lines in the book, it yields as each word. Sorry, I said that incorrectly. It yields as it hits each word. So I can run this. And now I'm going to attempt to utilize it. First, I'm going to create my queue, and then I'm going to pass my queue into my generator. So I have it there. And then the result that will be chapter of book. I run that. Now I've got my generator assigned to a variable called chapter of book. And then I can access my generator to output each chapter in the book. And so you can see it'll just get the next chapter of the book, and then will then access that queue which has just been filled up by the generator and print the item. So if I run this, the first chapter, the famous beginning of A Tale of Two Cities, it was the best of times, it was the worst of times. So it's got that entire chapter, word by word, in the queue, and I've read it off the queue. Now if I access my generator again, or run this again, I'm going to get the second chapter in the book. And I don't know who's already read A Tale of Two Cities. I will be honest and say that I have not. It's always been one that I thought I should read, but I've never done it. But each time I run this, I will get the next chapter in the book, because it's going to continue to load until it finds the next word chapter. That's kind of the simple version of it. Nothing super useful here, but again, I'm using a generator to grab a chunk of data from my input, process it, and then I'm outputting that piece of information, or that group of information, and then I can utilize my generator again to get the next group of information that I need to process. I want to note a couple of things here. I pulled down A Tale of Two Cities from Project Gutenberg, which I've done that before, so there's no surprise there. However, I did cheat a little bit and manipulate the text file to, first of all, it had like chapters in Roman numerals, and I didn't want to do that for this, so I changed all the chapters to numbers, like chapter 1, chapter 2, chapter 3. So I'm cheating a little bit there, cleaning it up a little bit. And then I had to double check to make sure the word chapter wasn't anywhere in the book, and it's not. The only time the word chapter comes up is actually in between the chapters, so that worked out well. I didn't have to make any edits there. And I added the line at the end that said end of A Tale of Two Cities, I believe, so that I would know when that was complete. Now, those kind of things aren't going to be available in real world scenarios, but I just wanted to keep this from becoming hyper complex, just to try to get this working. So I just want the one that you'll work with in the assignment is the one that I edited in that manner. Cut off all of the stuff at the end, because Project Gutenberg puts a whole bunch of boilerplate at the end about the book, and that was just going to cause issues. So just so you're aware. Okay, so that's the simple version of that. Now we can do more than that. Instead of just outputting the words, we could count them. So I've got a variable called chapter word count, and I'm going to try. So this is where I get that stop iteration where that's valuable. I'm using a try except. So once my generator is exhausted, it'll just print end of book, which is great because then I know that I'm done with my generator. But I'm going to try to grab the next chapter of the book. And then once that chapter of the book is loaded into the queue, which is what it does each time, I'm going to just get each word off the queue and count it. And then once the queue is empty, then I know I'm done counting that chapter. And I can print the chapter word count. And then once I get to the end of the book, it's going to print end of book. So if I run this, I think it's set up already. You can see each time I run this, I'm getting the word count for a different chapter in the book. And there's a lot of chapters, but eventually I'm going to get to eventually, like I said, it's a very long book. There it was. So it's a stop iteration. I went past it by accident. But I got the error because I had exhausted my generator, so I know I've been through the entire book. Okay, so now let's do it a little more. I don't know if elegantly is the word, but let's make it a little bit nicer. So again, I'm going to start with this time. I'm going to start with an empty dictionary, and then I'm going to start with chapter 1 and start with a word count of 0. And what I'm going to do here is I'm going to count all the words in each chapter of the book, and then basically append to my dictionary the word count for that chapter. So that I can see them all. And I don't think this one works in notebooks. I think I have this set up. Well, we can try it, but I don't think it will work. I didn't think it would. Well, let me do. Sometimes I have to recreate my generator if I forgot to. Got it there. Here's where I set it up. There we go. Let's see. Oh, okay. So there's chapter 1. Here's chapter 1 again. Well, that's not very useful. All right. Well, I guess I have one more step. So chapter 1, I'm showing that's how it outputs for chapter 1. That's not super useful. I guess I could have done a next there to get the next part. But anyway, so that's the syntax that I'm going to get out. Okay, so you can see again the first one's nothing's changed here, but I'm going to read through it, and each time I go through this function, it starts with an empty dictionary. And then, well, actually, it just does it once. So it starts with an empty dictionary, current chapter 1, current word count 0, and then I build up something that makes it a little more informative, saying it's chapter, and whatever current number chapter you're on equals the chapter word count. And then I continue to iterate that. So if it's not empty, get the word, oops, and then if it's chapter, that means we've reached the end of the chapter. I iterate chapter or increment chapter, and then start again at word count 0, and then I start with the next chapter. Otherwise, I just add 1 to the word count for that chapter. And then this is just a clear screen to make it visually nice, command prompt. And then I don't think this is necessary because it shows the current chapter word counts. And if it runs out of items in the queue, it waits. And then once it gets all done, it says program complete and breaks out of the loop. And then just down here, I've got the two processes, so I can run them concurrently. Now let's see if this will work nice. Writing and reading queue stream. Not yelling, sorry. And I've decided this is super slow because I'm continually clearing the screen, and I believe that's the part that really makes this slow. In fact, this is slower than I thought it would even be. Let's see if I put a false delay in there that I can get rid of. I don't have it here. Let me try saving this. Let me try to pull me out. No. All right. One more time. Yeah, it's just going to be slow. My computer's already chugging. So anyway, each time it goes through the loop, you can see it's iterating that count. If I didn't have the count actually printing, this would happen super fast. It's just because it's trying to print and clear the screen repeatedly that it's super slow. If you wait long enough, this will actually someday get past the first chapter of the book. And once it gets to the end of chapter 1, it will just start it'll be another dictionary item that says chapter 2, and et cetera, et cetera, et cetera. Again, just trying to show a simple writing to a queue, reading from a queue, and doing something of some sort of value. I'll let that just keep running in the background. So that's that one. And that is actually the last one of those I wanted to show you, other than I wanted to show you how the assignment setup looks for the last assignment. So I'm going to show you what the assignment setup looks like. If I go over to topic 3 here, I don't know who's all looked at it, but for topic 3, I'm asking you to do something similar to what I just showed with reading A Tale of Two Cities. But in this case, I'm actually going to have you read a queue that is 2 books. I've got Dracula and A Tale of Two Cities that are going to be put into a queue, and then your job is going to be to read them off the queue and just get the total word count of the book. And to make this not super annoying, because this took me a while to get this working correctly, I've actually created the first half of the program. So you know, all this stuff from before. In this case, I've got a couple of functions here. The first one is stream 2 books. That takes a book stream queue, and it has 2 functions inside of it. You can see stream 2 cities and stream Dracula that read the 2 books. And they are each a thread. So they run, as we know, essentially concurrently, but not quite. So both books are being put onto the same shared queue at the same time. They're just getting loaded up into the queue, and then I just, down here, you're going to see it's going to print it out, but when you do your part of that, you wouldn't necessarily want to print out the queue. And then this is the part where you need to write your code, because I'm asking you to now read that queue as it's being written to do word counts. And you need to parse out the 2 books. So each one is going to be, you'll see when I run it, each one is going to be identified with the book title and then the word, so that you can read it, determine which book it's from, and add it to that word count, because they're going to be all mixed up, because we know they're getting put onto the queue as fast as they're getting read. And then down here, once you have your part of it created, you would need to uncomment this one and this one to start. Otherwise, your reading queue will never happen. So I'm going to run this. Let's see if the other one actually finished the chapter. Nope, that's annoying. All right, so kill that one off. Python. So I'm going to show you what that code will do if you run it as it's right at Blackboard as a copy paste. So this is the output that you're going to be handling from the queue, and you can see for some reason it's just getting 2 cities right now. I might have it set up where they're not happening concurrently or something, but you can see that each word is a dictionary item with an identity or an identifier and a word, and you can count them based on the key. So you would just read each one off of the queue and count it. If it's 2 cities, you count it on the 2 cities word count. If it's Dracula, you count it on the Dracula word count. I'm kind of annoyed that the other one isn't running. I'm not sure why they're not both showing. Did I not? Oh, I think I may have commented out one of the prints. So anyway, that's what I'm asking for in that last assignment. Hopefully it doesn't give you too much issue because I've built that first half and tried to create the structure for you. Okay, so that's that one. The other assignment, if you haven't already noticed the announcement this morning, I tried to ask you to do something that would take you, I guess, until the heat death of the universe to get done, trying to determine the first 33 Fibonacci primes is turns out super difficult. I had an error in my solution that actually it was giving me ones that weren't actually Fibonacci primes. So I thought it was going to work for everybody. I was mistaken. So this morning, or yesterday morning, I updated that assignment. So it is only going to ask you to get 4 groups of 4 Fibonacci primes, or three groups of 4 Fibonacci primes, because you can get to the 12th Fibonacci prime without it being completely ridiculous, but when you try to get the 13th one, it takes forever. So hopefully that will help. To those of you that beat your head on the wall on that one for a long time, I do apologize. I've actually I want to try to solve that myself now, because I'm sure there's a more efficient way to do it, and I'll do a bit of research. But for the assignment parameters, hopefully what I've asked you now to do, the whole point of the assignment is to demonstrate the usage of a generator, so you'll be able to do that hopefully without too much difficulty. So those are the two assignments that are like normal assignments that I'm asking you to do, and then the other item is getting me your final project proposals. So I need you to get those in so I can give you any feedback that's necessary on them, and then you can get started working on them. And that's it. That's what I have for today for new material and for the semester for new material.